So the singular value decomposition of the operator t shows us how we can use the singular values to really describe like what the action of t is. So suppose that we've got the singular values denoted by sj's here. These are the singular values of t. Then there exist two orthonormal bases, an orthonormal basis of e's and another one of f's, such that t applied to v is given by this formula right here. And we'll talk a little bit about what this formula means in a moment. But you can see that first we are projecting v to the e basis to take its e coordinates, and then we scale by the s's, and then we attach this to the new orthonormal basis on the outside. All right, so first let's look at the proof. So the first observation is that square root of t star t is positive and hence self-adjoint, as we've noted before. So we know that, and let me say, we know that v has an orthonormal basis of eigenvectors of root t star t. And there'll be a full complement of them, meaning that we have as many of them as the dimension of our vector space. Okay, so let's see. Now, if we look at the decomposition of v with respect to this ONB, this implies that when we apply root t star t to v, we're going to get by linearity, it will factor through the sum, and we'll have t star t applied to ej, which gives us this. All right. So now, since we know that t looks like s times square root t star t for some isometry s, if we look at t applied to v, so then this is going to be s root t star t applied to v. So we can apply s to this thing that we had in the line above. And again, since it's linear, we can pull all of the scalars out front, and it'll just go right through and munch on the vector living at the back of that sum there. And so this is sj, and then the projection onto ej. And then since s is an isometry, it's going to map one orthonormal basis to another. And that was by, oh shoot, which one was that? 742. Okay. And so that's it. That's all there is to it. Okay. So what's this really saying? So what this is telling us is that if we are given a linear operator, we can find an orthonormal basis E1 through En and another orthonormal basis F1 through Fn, such that if you apply T to any operator, to any element of the orthonormal basis, then it's just going to be, that's going to get mapped to a scaling of the Fj basis by the corresponding singular values. And by choosing things nicely, these will always be non-negative. And so you can think of this as like a super duper upgrade from like once upon a time we saw a theorem that said, given a linear map from V to W, and we know that we can always find a basis of V, then we can always think about this mapping in terms of what what T does to this basis. I guess I should have said so we talked about this as a way to define a linear map. So now what we're saying is that you can do this with orthonormal bases instead of just regular bases whenever you're in an inner product space. And you can actually do it in a really nice way, so that, so this formula above holds with where the scalars are non-negative.